Okay, here we go. This is the last lesson on series convergence or divergence. There's one last type of series that is important and easily distinguishable. You can quickly tell it's this kind of series. If you see an alternating series, then you can apply the first nth term test, skip any other tests, and go straight to these tests. So it's nice that whenever you see this, you will clearly know what to do, but it requires a little bit of work. So where are we? We are here now, box 3. And that is if you see an alternating series. An alternating series will identify as anything that goes back and forth between positive and negative, and you're going to see that by -1 to the nth or -1 to the nth, n plus 1. And so we will learn that all alternating series converge mostly. We'll check 2 quick tests, but I think you're usually going to find they all do. And then we can say some specific types or things about its convergence, and then we can actually calculate how far away a certain number of terms of adding up of that alternating series is from the actual value. So up to this point, geometric series are the only series we can actually find where the series converges to. Alternating series, we won't find what the series converges to, like the number it adds up to, but we can find out how close we are to that number. So there's a bit to do here. Let's jump in. An alternating series is any series where the terms alternate between positive and negative. To achieve this, the series will have -1 to the nth or -1 to the nth plus 1. Just like any other series, the alternating series will automatically diverge if it meets the nth term test, so if the limit does not equal 0. So if you get that on an alternating series, you just stop and you say it does not diverge. But what's interesting is this. An alternating series will converge if we equal 0 on the nth term test. Now notice this is the first time that equaling 0 on the nth term test tells us convergence. So, but there's one other twist. It also has to, the alternating series has to meet this second thing in letter B. The next term always has to be less than or equal to the previous term. So for instance, if we have a series 1/4, 1/5, 1/6, ... See, the next term is always smaller than the one before it. 1/5 is always smaller than 1/4. Or we could say 1/6 is always smaller than 1/5. So that's important, and sometimes we'll have to show that, and other times we won't. And let's keep reading. You will usually determine A above the nth term test when you apply the nth term test, which you'll basically do to every series anyway, unless you can automatically see it's a P series or geometric series. But to determining this letter B, this next term is smaller than the previous one or equal to it, that requires a little bit of work. Number 5, another way is to say that B, another way to say that B, that second part, is that every value in the series is less than or equal to the value before it, or that the values in the series are always decreasing or remaining the same. And there are actually like 4 ways we can do this. And there's a chance on a free response question you might be asked to show that an alternating series is convergent. And so you would show the nth term test equals 0, then you'd have to use one of these methods. You might be able to flat out show that the every next term is smaller than or equal to the previous term. Or you can subtract the previous term to the left side and show that subtracting them is always going to be less than or equal to 0. Or you can divide them, and that number has to always be less than 1 or equal. Or I guess maybe if you really love this, then you can find the derivative of your term and show that the derivative is less than 0, right? So if the derivative or the rate is decreasing, then all the values after are going to be decreasing. Less than or equal to 0, it could remain the same. So we will practice all of this in just a minute. But I want to go ahead and move on to the next part before we throw in a practice problem. So where are we? So in our boxes here, we see an alternating series has that -1 to some n or n plus 1 power. And we know they almost always converge. But if we're asked to check if it converges, then we have to show the nth term test equals 0. And we have to show the next term is always less than or equal to the previous term. Now, honestly, that's usually not the most interesting thing about alternating series. It gets more interesting on this next part, called absolute or conditional convergence for an alternating series. We've already said that most alternating series are in fact going to converge, but then we can know something specifically about it. We can say that the series absolutely converges or just conditionally converges. And it goes something like this. Sometimes it's easy enough, number one, sometimes it's easy enough to show that the alternating series converges. However, sometimes we're asked to tell a little bit more about its convergence. So, we will compare our alternating series with its non-alternating counterpart. That's a fancy way of saying we will ignore the -1 to the nth, or -1 to the n plus 1. So in other words, we'll take away the alternating expression and just examine the original function without the alternating part. And then here's what we learn. If the series without the alternating part still converges, then our alternating series is called absolutely convergent. But if the series without the alternating part diverges, then our series is called conditionally convergent. Our series only would converge because of the alternating part. So if we took it out, it's a divergent series. The alternating part is still convergent, but we say it's conditionally convergent, meaning that it didn't stand on its own without the alternating part. Now, so here's what's going to happen, and this is why this lesson is last. You're going to have to tell absolute or conditional convergence, you're going to have to take out the alternating part and just look at the original series. And so, number 5, the series without the alternating part can be any type of series that we've seen. And you'll have to apply any of the tests that we've seen to determine that part's divergence and convergence. So you take out the alternating part, maybe you have a p-series, maybe you have a geometric series, maybe you won't have either of those, and then you have to run through your tests. We already did the nth term test, so then maybe you're going to have to do the ratio test. Hopefully that's what you have to do. Or maybe the integral test, or the direct comparison test, the limit comparison test. You need to know all your tests, and I'll tell you what, alternating series are a big part of an AP exam because they can also test all these other tests as well. Finally, if an alternating series is absolutely convergent, then you can rearrange the terms. Maybe put all the positive parts together and negative parts together, or find positive and negative parts that cancel each other out, and you'll still get the same value as the original series. All right, so before we talk about the last part, let's look at an example of an alternating series and how this works. So we'll do a very simple one for our example. So here's the alternating part, -1 to the n plus 1, and the rest of the series is 1 over n. So first of all, here's what you do. The instructions will say, does this series converge or diverge? And if it converges, is it conditionally convergent or absolutely convergent? So I see it's an alternating series, so that's a check in my head. So now I know I need to do 2 tests. I need to do the nth term test. So the limit as n goes to infinity of the non-alternating part, and that equals 0. And okay, so that means that it's probably converging. The other test is to show that every term is less than or equal to the term before it. Well, let's see if we can figure that out. So 1 over n plus 1 has to be less than or equal to 1 over n. We can cross multiply times 1 on both sides and get n is less than or equal to n plus 1, and we can see that's true, right? That's good enough to show it. If you want to subtract n on both sides, you can show 1 is greater than 0, and so that's true as well. So I know that this converges. Okay, it's called the alternating series test. You can abbreviate or we'll say converges by the AST, alternating series test. But the instructions will usually not just ask for convergence. It'll usually ask, does it conditionally or conditionally converge or absolutely converge? So now what we want to do is we want to take the non-alternating piece and we want to test this. So here we go. I see that this is a harmonic p-series, right? It's 1 over n to the first power. That's a harmonic p-series, or any p-series where p is greater than or equal to 1. is divergent. So any P series where P is less than or equal to 1 is divergent. So this is equal to 1, so this is a divergent P series. Now, that doesn't change our original alternating series to divergent, but a divergent non-alternating part of our series means that our alternating series is conditionally, well, I'll tell you, let's call this A sub n. So we can say, so A sub n is conditionally convergent. And there you go. That's important. That we have now told if it's conditionally convergent or absolutely convergent, because we tested the non-alternating part using all of our series tests, and our non-alternating part diverged, so that made our alternating series conditionally convergent. If our alternating part converged, then we'd say it was absolutely convergent. All right, now, you need to practice these, because this also helps you practice all of your other series, because you might, to test the non-alternating part, you might have geometric series, P series, you might use the ratio test, you might use the integral test, you might have to use a comparison test. So practice, 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 check your answers, look at your work, and then figure these out. All right, now there's one other thing, and this gets really interesting and very useful. Here we go. This last part is very important and often appears on the AP Calculus BC exam. We'll actually use this last part later in the course as well, so this is an important idea. Okay, remember, I've been saying it on probably just about every video. We've only been able to determine the convergent sum of a geometric series. That's the only one we can actually find out what it adds up to. Now, that sounds like we're going to find it on this next one, but we're not. While we won't find the convergent sum of an alternating series, that's kind of sad, we do have a way to find out how far from the actual answer our convergent sum is. So this is interesting, because we still might not know what the actual convergent number is, but we can know that we're close to it. We can know how close, within a range of how close we are to it. So let's keep reading. Suppose we'll find the value of a finite number of terms of an alternating series. So maybe I would say S of 4 means we're going to add up the first 4 terms of this alternating series. So what we're going to do is whatever that adds up to, okay, that's going to equal some number, okay, whatever that adds up to, if we could find the actual sum to infinity, okay, we'll just call that S, then our number subtracted from the actual sum, and take the absolute value, we don't care if it's positive or negative, gives us what's called a remainder, right? I mean, that's just good old math, right? You take one thing away from another thing, you have a remainder. So this is saying the true sum of the series to infinity minus our finite sum, so if we only add up the first 3 terms, 4 terms, 5 terms, that gives us a remainder in absolute value signs. We don't care if it's negative. Now, here's what's really, really cool about the remainder. And it might be really cool if you take a college calculus class or want to on your own, like work on a proof of why this is true. Here's the cool part. That remainder, so how much is left over between the real sum and our partial sum, is always less than or equal to the absolute value of the next neglected term of the sum. Next neglected term. So you take, if we are going to find the partial sum of the first 4, then we are going to figure out, well, what is the 5th term in that series? And our remainder is always going to be less than or equal to that. So that means that our remainder is always less than or equal to the next term that we didn't use in our finite series. So stated all together, the difference between our partial sum and the actual answer is called a remainder, and that remainder is always less than or equal to the next term we didn't use. Now that's interesting, because we won't know S. We don't know the actual sum. But we can find out that the next term maybe is like 0.012. And so that means that whatever our partial sum adds up to, let's say adds up to 5, then the total sum is going to be within 0.012 of that 5. And in fact, we could take that 5 and we could add 0.012 to it, and we could subtract, well, this is really bad math notation. We could subtract it from it, and we could say, okay, 4.988 between, and then we could say the actual answer is between 4.988 and 5.012. So we get a very, in some cases, a very small range of possible answers of the actual infinite series, which is cool because geometric series are the only series that we've been able to actually pinpoint the convergent number. But now in an alternating series, we can pinpoint usually a pretty small range that the convergent number has to be within. I'll show you how to do this in a second. There's one more thing that we can do with it, and I'll show you that as well. Sometimes we're asked to determine how many terms we're going to add up. So here, this example, I added up 4. But sometimes it might want to know how many it takes to show that the value of your finite series, so your partial sum, is within a certain error. So it might say within a thousandth or 10,000th or 100,000th of the actual value. So in that case, you will plug in n plus 1 into your series and set that less than the error to solve for n. I'll show you this in a second. All right, so here we go. Let's work through one of each of these, and we'll be finished with the video. So let's say that we have this finite series from 1 to infinity. Not finite. I'm sorry. This infinite series, alternating series, negative 1 to the nth power 1 over n. Okay, so let's find the sum of the first 4 terms. So I'm going to plug 1 in for n, so negative 1 to 1 over 1 over 1, plus 2n for n, negative 1 squared over 1 over 2, plus 3n for n, and 4n for n. Now, I'm stopping here. I'm not going to infinity. This s sub 4 means find the first 4 terms. So what do we have? Negative 1 plus 1/2. Negative 1/3 plus 1/4, right? That alternating piece just changes the sign back and forth, back and forth, back and forth. And so I'm going to take a calculator and I'm going to add up those numbers and figure out what we have. And I messed up my calculator, so let's try this again. All right, and we should get, oh my goodness, messing up all over the place, negative 0.5833. Whoops, I lost my negative. Negative 0.5833. So the sum of the first 4 terms, that's called a partial sum, is negative 0.5833. Well, we want to find out how far away that is from the actual sum. Okay, so remember, the actual sum minus our partial sum, the absolute value of those is called the remainder. And the remainder is always less than or equal to the next sum. Or I'm sorry, the next term that you didn't use. So if we did 4 terms, then we're going to find out that the remainder of the fourth, after 4 terms, is going to be less than or equal to the 5th one. I don't know why I put this plus 1 goes down here. Sorry about that. All right, so what is the 5th term of our series? So here we go. The 5th term, negative 1 to the 5th power, 1 over 5. That is negative 1/5. So negative 0.2 is our 5th term, which means that 0.2 is greater than or equal to our remainder. So our remainder, so what that means is that our partial sum of 4 terms is within 0.2 of the actual answer to this series added up to infinity. That's kind of cool to know. Now we can create some bounds. So we can take our partial sum, negative 0.5833, and we can add 0.2 to it, and we can take negative 0.5833, and we can subtract 0.2 from it, and that'll get us a range of all of the possibilities that could be the sum of this series. So negative 0.3833, negative 0.7833. So we have a range of possible answers. You might be asked to find a range or an error bound, and this is an error bound. That's really cool. That's super useful. So what else can we do with that? Well, honestly, being 0.2 away sounds close, but it's really pretty far. So the last thing that you might be doing is you might be given a series. So here's an alternating series, n equals 1 to infinity of, let's do negative 1 to the n plus 1 over, say, n squared. And it might say, you know, find out how many terms, so that's n, right? So how many terms, so your error is within, or no, let's say less this time, less than 1,000th off. So we want our error to be less than 1,000th off. So we're going to take the non-alternating part, because the alternating part, we're going to do the absolute value of this, it doesn't matter. Remember, our remainder, the absolute value of it has to be less than or equal to the next term. Okay, so what that means is that we want all of this to be, well, not less than or equal, we want it to be less than 1,000th. So let's find what our term, the next one will be n plus 1 squared. We want to find out how many n's it takes for that to be less than 1,000th, or 0.001. You know, this probably be written as a decimal in the instructions, and then you would change it to 1 over 1,000. Because now we can cross multiply, you get 1,000 on the left side, n plus 1 squared on the right side. We could take the square root of both sides. Square root of 1,000 equals n plus 1. We can subtract the 1 to the left side. And then we can go ahead and take the square root of 1,000 and then subtract 1 from it. And we find out that n needs to be greater than 30.622, which means we need 31 terms in order to guarantee that this series will add up enough so that its error is less than 1,000th away. This is a fairly common type of AP exam problem, so you'll want to practice this as well. Okay, so where are we? Where in the world are we? We have finished finally all of the roadmap. Today we looked at alternating series specifically. They almost always converge, but you have to show it. You show the limit is does equal 0 on the nth term test, and every term is less than or equal than the term before it. Then you might want to say which type of convergence do we have. You test the non-alternating part, and if it converges, you're absolutely convergent. If the non-alternating part diverges, you're conditionally convergent. And then finally, we can find the alternating series error bound. So we can find, we can use this to find out how far away our answer is, and then we can actually add and subtract that from our partial sum to get how far away, you know, a range for the true sum. Or we can be asked to find the number of terms it takes so that our error is within a certain number. All right.